Welcome again, everyone. Now, we will be discussing about coplanar forces. Previously, we have discussed the basic operations of vector. Now, we are going to apply vectors in coplanar forces. So, to start with, let us define forces in same plane or coplanar forces. So, there are two systems. The first one is the concurrent force system, and the next one would be the non-concurrent force system. So first, we will discuss concurrent force system, which are all forces intersect at the same point or all forces originate at common points. So here's an example of two-dimensional force system that is concurrent. So we have three forces in two-dimensional plane. They are all concurrent. And for a three-dimensional force system, we have also three forces that has a common point O. So that is the concurrent force system, meaning they originated at a single point or they intersect at a common point. So let's define force. It is the term assigned to mechanical interaction between bodies, and force can affect both the motion and the deformation of the body on which it acts. But since our subject is statics of rigid bodies, the deformation due to the force applied on a body would be temporarily neglected. The effect of the deflection of an object or a non-rigid object would be discussed in the next subject, which is strength of materials or mechanics of deformable bodies. So there are two types of force: a contact force, which is distributed over a surface area of a body, like the bearing force between your toe and the floor. So if you walk on the floor, the force between your toe and the normal force exerted by the floor is called the contact force, and the distance force is distributed over the volume of the body. So your weight is a form of distance force. This is because of the gravity or the acceleration due to gravity caused by the earth. So force can be of three types of vector. So it could be a fixed vector wherein equivalent vectors have the same magnitude, direction, and point of application. Could be a sliding vector wherein equivalent vectors have the same magnitude, so it's the same with fixed vector, direction, but the line of action is the common thing about sliding vectors. And free vectors, they have the same magnitude and direction only. So for fixed vector, they have magnitude, direction, and point of application. For sliding vector, they have magnitude, direction, and line of action. For free vector, they only have magnitude and direction. But the point of application could be different and the line of action could be different. So let's appreciate that later. So a force is applied so small that it may be approximated by a point, in which case the force is said to be concentrated. So the point of application of a force is in a differential area, and the line of action of the force is as shown in this red dashed line. And let's have here a fixed vector. So a fixed vector has the same direction and magnitude and also same point of application. If you have here force P applied at point A, and the direction of P is to the left, whereas if you apply point P at A and the direction is to the right, and you apply another force P here for member A, which is directed to the right, as you can see, this body, if this is non-rigid object, this will tend to elongate. Okay? But if the direction of the forces are reversed, since the direction of P at A here, originally directed to the left, is directed to the right, and the force P here is directed to the right and is switched and is now directed to the left, this causes now compression to this object. Therefore, if these two forces are interchanged, they have different effect for a non-rigid object, because this one will tend to elongate while this one will tend to shorten or to be compressed. So for a non-rigid body, the point of application of force is very important. But for a non-rigid body, if you change the location of P but it has the same magnitude and application, or you simply change the point of application, or you interchange the point of application of this 2P, this will not affect this will not externally affect the body. They would have the same resultant, which is 0. But for a non-rigid body, this would cause elongation and shortening. Now, if this force is placed at point A, say for example this P and this other P is applied at A, for a non-rigid body, this will yield no deformation. But for a fixed body or a rigid body, the different application of forces would have no external effect, and this is the principle of transmissibility. A force may be moved anywhere along its line of action without changing its external effect on a rigid body. Now let's have the component of a force. It would be helpful for us to know the component of a force in rectangular coordinate for us to analyze the resultant. So later we will appreciate the application of component if we get the resultant of component, the component of the force. So a force vector has a direction, oftenly represented by direction cosine. So the direction cosine here about the x-axis is theta x. So we have vector f in the first quadrant and its direction cosine as theta x. Now, it has two components, or f could be represented by fy and fx. Now, if you want to use its component, you might want to omit the force. So if you use the component, make sure you eliminate the force. Now, if you try to use the force, the resultant, now you have to eliminate the component. So you have to choose if you will use the force or you will use the component. Now, how do we get the component of a force? So first one is by using trigonometry. So obviously, from trigonometry, fx is equals to f cosine theta. Likewise, if you want to solve for fy, you will use sine function. So that is fy equals to f sine theta x. But in some other cases, theta y is given. Therefore, we can solve fy as f cosine theta. So if you have viewed or if you have reviewed the previous videos of this lecture series, you will understand why theta y is used for representing a vector f. That's why I use theta y instead of theta x. However, you could use both theta x or theta y in analyzing the component of a vector. Now recall from vector analysis that a force vector can represent its component by its unit vector. So if this is the force vector A, therefore force vector A is the product of the magnitude of vector A and its corresponding unit vector. So we have the force and the direction cosine. So the direction cosine is cosine theta x, is this one, for the x component of vector A. Now for the y component, they use cosine theta y, which is the direction cosine. Now the same case goes for the z-axis. So we can now say that to get the component of a force given an angle, we can simply use F cosine theta x, F cosine theta y, or if it is theta x that is only given, we can still solve for Fy in terms of F sine theta x, F cosine theta x. So whichever method you want, as long as you get the value of the component, it's okay. So now let's proceed. If force passes at a certain point, so the direction of force is defined by 2 points. So we have here a vector F or force F passes at 0, 0 and 3, 4. And by analyzing the slope of the line of action, we have the slope as 4 minus 0 and 3 minus 0. So that is 4 and 3. And this unit could have been analyzed in a triangle. So therefore, the hypotenuse of a right triangle with 3 and 4 legs would be 5. So now by Pythagorean theorem, so there we have it. Rx is 3, Ry is 4, and R is 5. And from trigo also, we can say that Rx is equals to R cosine theta x. Now let's have it here. Rx is equals to R cosine theta x. And also recall that we have discussed just a while ago that Fx is equals to F cosine theta x. And therefore, we could solve for cosine theta x. From this equation, cosine theta x is equals to Rx over F. And also, cosine theta x is equals to Fx over F. Now we can say that Fx is equals to Frx over R. And similarly, we can say that Fy is equals to Fry over R. So if a vector is defined by its points or defined by where it passes, so we can say we can get the component by analyzing its slope. So first we get the slope. So we have the run equals to 3 and the rise equals 4 depending on the inclination of the force. Then you simply get the hypotenuse of that slope, and to get the x component, multiply the magnitude of that force, and if it's an x component, you multiply it by Rx divided by R. So for Fy, if you try to use the y component, again multiply it by F or the magnitude of F times Ry divided by the R. Okay. So it also applies for a z-axis where your Fz would be F times Rz over R. And we could prove that by using the unit vector. So recall from vector analysis that the direction cosine x is equals to the displacement about x-axis over its total length. So we can say now that Rx is simply the change in or the displacement about x-axis, that is 3 minus 0. So please watch the video about vector representation. You will learn about this unit vector and how this direction cosine is represented in this manner. So therefore, Rx over R, it satisfies the principle of vector. Now we can say that the unit vector is simply the change in x component, the change in y component, and the change in z component over its magnitude. So this is a representation of a unit vector. And also, as you can see, the magnitude of the first vector is simply multiplied by the unit vector, which gives the direction to the vector quantity. Now, as you can see, this is multiplied and this is multiplied. So that is the x component, the y component, and the z component. Now, as you can see here, it does the same thing. You multiply the magnitude times the direction, magnitude times direction. Okay? So there you go. So in summary, the components of a force could be determined by either analyzing its angle or by analyzing its slope. So if the angle is given, we use trigonometry, And if the slope is given, we can use ratio and proportion or by vector. And this formula also applies to y-axis and definitely also applies to the z-axis, which uh, we will discuss on later part of this course about the three-dimensional analysis of concurrent force system. This topic only includes coplanar forces for concurrent and non-concurrent forces. Now, let's discuss the resultant force. So what is a resultant force? Forces in plane have resultant force. So if we have several sets of force or a force system that is concurrent, they could be added to form a one force which we call resultant. So the resultant force is also called the net force. So to fully appreciate that, if a ball is kicked by two persons simultaneously, so there are two forces acting on the ball, but the ball will eventually move only in one direction, and that is along the line of action of the resultant force of the two force caused by the kick. So if we have several forces applied on an object, this will lead to one resultant force, and the movement of that object is based on the direction of the resultant force. Now, what are the steps to determine the resultant force of coplanar concurrent force system? So later, we will discuss the resultant force of coplanar non-concurrent. Now, we are just dealing with concurrent force system. And again, when we say concurrent force system, they originate from a certain singular point or they have a common point. So for this topic, we will need to get first, we will need to know the step-by-step procedure in determining the resultant force. So the first one is to determine all the x components. That's why it is important to get the it is important for us to be knowledgeable in determining components of a force because it is one step in determining the resultant. So we will first get the x component of the force. So if we have here a force defined or described by an angle or by slope, we can simply get the x component. So for example, F1 has an x component, so we can get F1x if there is a slope. And also we can get F2x if there is an angle. So we have discussed how to get the x component by slope or by angle. And next, determine all the y component of each force. So these two steps could be interchanged. You may want to get first the y component and then go to the x component. So whichever you want. So this step 1 and step 2 could be interchanged. So say for example, we have F1, you need to get the F1y and the F2y and F3y. Now, if you have the summation of all the forces along x, you should represent that by sigma fx. And if you have the summation of forces along y, you can get that by using the notation summation fy or sigma fy. Now, the next step would be getting the magnitude of the resultant. So if you try to draw the summation of forces along x or sigma fx and sigma fy, take note that they are sign sensitive. Now, if your sigma fx or the summation of forces along x is negative, make sure you draw it to the left or to the negative side of your x-axis. If you get the summation of forces along y in the positive direction, make sure you draw it in a positive direction. If you get a negative value, make sure you draw it downward for us to easily get the angle or the direction of resultant, because this will lead to error if you have failed in drawing properly the orientation of the sigma fx and sigma fy. Now, by trigonometry, for example, if we have sigma fx here and sigma fy, to get the value of the resultant or the magnitude of the resultant, you can simply use the Pythagorean theorem, wherein the magnitude of the resultant for r squared is equals to the magnitude of sigma fx squared plus sigma fy squared. Now, you can now have r if you know sigma fx and sigma fy. That's why getting the component is vital in getting the resultant because uh, it's also the same way na how you get the component from the resultant. You're just reversing the process. Now, to get the direction of the resultant, it is best to draw sigma fx and sigma fy. Now, it is easy for us to get now the angle of the resultant force by using trigonometry. So, there are different cases. So, if your sigma fx is a negative and your sigma fy is positive, you can get this angle using tangent function, and then you can get this one by subtracting 180 from the angle you have determined. Then you now have the direction of r measured from the positive x-axis. Now for the standard, we have to measure the angle of the resultant vector from the positive x-axis. Now what if you have the same negative answers for sigma fx and sigma fy? The same, you simply just draw it in the proper direction, then identify the angle, then make sure you measure it from the positive x-axis. Now, if you want to measure it the other way around, always take note that if you measure it clockwise from the positive angle, that is a negative measurement. Now, if you have positive sigma f and negative sigma y, and the same case goes. Okay? So a concurrent force system which has zero resultant force in equilibrium. So if you have several forces acting on a certain point, therefore it's a concurrent. But if you determine the resultant and you get zero, therefore that object is in equilibrium. So summation of forces along y is zero, and summation of forces along x, I'm sorry, this is summation of forces along x, and summation of forces along y is 0. Now, if you have computed for the resultant, let's discuss equilibrant. So when the resultant of force system is not 0, definitely it's not in equilibrium. If the equilibrant vector is included in the system, the net force would be 0. Or that means the system would be in equilibrium if equilibrant is added in the system of forces. Therefore, we could say that the equilibrant has the same magnitude with the resultant, but it has opposite direction. Okay, for the appreciation of this subject, let's have an example. So we have here 4 forces, F1, F2, F3, and F4. And it is required for us to determine the summation of forces along X. So F1 is represented by an angle, F2 by slope, F3 by an angle, and F4 by a point. However, it could be determined by simply getting the slope of the vector. So let's start. So using vector method, again, now we will use two methods in determining the resultant. The first one, we will use vector, and the next one, we will use scalar method. So let's start with the vector method. So for the concurrent forces, it could be represented in vector form as follows. So let's represent each force in a vector. So to get the representation of F1 in vector form or in 2D vector, so F1 is 40 cosine 30i plus cosine 60j. So if you have trouble in following us in getting the vector representation of F1, I suggest you watch the video to learn more about vectors, because I will not discuss how to represent vectors in this topic. However, I will also try to, as much as I can, to teach you how it is determined. Okay, so F1 is represented by 40 cosine 30i cosine 60j. This is because the direction angle, direction cosine is the coefficient of I, and the direction cosine about y is the coefficient of j. Now F1 is 34.64 10i plus 20j. As you can see, this is simply the x component of F1, and this is the y component of F1. So this is the vector form. Vector form is simply by representing its component. So that's the difference in scalar method. Now we get F1. Now to get F2, or to represent F2, that is the magnitude of F2 and the unit vector of F2. Again, this has been discussed in my previous lecture series. Now we have to represent F2. Now F2 is negative 18i plus 24j. And the rest should be written. So how to represent F3? So we have discussed that, and how to represent F4. Now we have 4 vector representations of F1, F2, F3, and F4. Now we are asked to get the sigma fx, or the summation of the x components of each force. So to get that, the resultant vector is the sum of all the vectors above. So how to add vectors is simply adding all the i's and adding all the j. So adding all these vectors f1, f2, f3, f4 leads to the value of their resultant vector. So adding the vectors now, we have the sum of this term is equal to 30.23991, and the sum of the j terms would be this one. Now we can say that the resultant has the vector form r is equals to 30.2339i minus 11.7446j. Now sigma fx is the coefficient of your base vector I. So there we have the answer for this question, or the sigma fx. Now let's try the scalar method in determining the x component of each forces. So for F1, we can use the cosine function. Now we are using scalar method to check if the vector method is correct. So just another way of solving the sigma fx. So F1x is the x component of F1. So by trigonometry, we can say that F1x is simply f cosine 30. And substituting the value of f, that is 40, we have 40 cosine 30, that is equal to 34.6410 kilonewton. For F2, since the slope is given, let's have the hypotenuse of the small triangle. So 3, 4, the hypotenuse is 5. If we are solving for the x component, multiply the magnitude by 3 over 5. If you want the y component, multiply the magnitude by 4 over 5. But since we are asked with x component, we simply multiply the magnitude 30 times 3 over 5. But make sure you write negative sign. Why? Because this is oriented to the left, or the x component of F2 is obviously to the left. That's why F2x now is negative 18 kilonewton. Now for F3x, we use the this is 20. This should be sine 45. However, you may still use cosine because the angle is 45. You will leave this with the same answer. But for the standard, we use sine because this is the opposite of 45. So negative 20 sine 45, that is negative 14.1421. And as you can see, this point could tell the slope of this line, so that would be 2 and 3. So the square root of the square of 2 and 3 is square root of 13. Now if we want to get the x component of force vector F, we multiply its magnitude with 2 over square root of 13. So please neglect this cosine. That has been wrong. So now the value of f or x would be 27.7350 kilonewton. Now adding up all the exponents yield us to the value of sigma fx, that is 30.2399 kilonewton. That is similar also to the value of the coefficient of the base vector I using vector method. Okay, so now we get the sigma fx. Now the next question, or the next problem asked, is the summation of forces along y, or sigma fy. Now since we have the resultant vector already represented by base vectors I and j, the coefficient of the j base vector j is sigma fy, because again r is just the vector r is represented by its component. Now, if you are writing a force in a vector, it is written by showing its component about the axis relative to what is their base vector. So the sigma fy for this resultant vector is the coefficient of the base vector j, that is negative 11.7446 kilonewton. Now let's try to use scalar method, that is simply trigonometry. So if you want to get the y component of f1, we use sine function. Therefore, 40 sine 30, we have f1y equals 20 kilonewton. And for f2, we want to solve for the y component. So that is simply multiplying the magnitude. And if you want to get the y component, so that would be the rise over the hypotenuse. So 4 over 5, we get f2y equals to 24 kilonewton. For f3y, we use cosine. I'm sorry, that this should be cosine. However, this is 45 degrees. That's why the answer is still the same. So make sure you write the negative sign because f3y is directed downward. So that is negative 20 cosine 45. We have negative 14.1421. And similarly, if we have here the 2 and 3, if we want to get the y component of f4, that is simply the magnitude of f4 times the rise and the hypotenuse. Remove this cosine, I'm sorry. And the value now of f4y would be negative 41.6025. Don't forget the negative sign. And adding them up yields to the value of sigma fy, that is negative 11.7446. So that is the same with the value of the coefficient of base vector j. Okay? So now, the question is to determine the magnitude of the resultant. And using the vector method, we have now the vector r represented by this equation. So to determine the magnitude of the vector, recall that we simply need to get the square root of the sum of the squares of its components. So again, if you want to learn about vectors, I have uploaded videos for this topic. Now we would like to get the magnitude of vector r, or the resultant force. So that is just simply squaring this term and squaring this term, adding them up and getting the square root. We get the magnitude of vector r, that is 32.4349 kilonewton. Now for scalar method, since we have already determined summation of forces along x and summation of forces along y, take note that we have a positive value of summation of forces along x and a negative value of summation of forces along y. Make sure you've drawn it the proper way, and we get, substituting the values of the components, we have 30.2339 squared plus negative 11.7446 squared yields to the value of your r, which is equal to, I'm sorry, it's not shown here. You will get the value 32.434. As you can see, they have the same solution. Okay, now for the direction, we can use the unit vector. So the unit vector again is the quotient of the vector and its magnitude. So if we divide the vector by its magnitude, we can get its direction, the unit vector, or the one that gives the direction to the vector. Now, if we have the unit vector, we can get the direction cosine. So this is the direction cosine measured from the x-axis, and this is the direction cosine measured from the y-axis. If cosine theta x is the direction cosine or the coefficient of base vector I. So cosine theta x is 0.9321. Therefore, theta x or the angle measured from the positive x-axis is 21.2289. Similarly, if you use cosine theta y, you use this one, the value of this one, 0.3621, you get theta y equals to 111.2292. Now, if you're using scalar method, you simply need to draw sigma fy and sigma fx. Then by trigonometry, you can say that theta x is the tangent function. So tangent theta x is equals to sigma fy over sigma fx. And solving for theta x, we now have theta x equals to negative 21.2290, which is similar when we are using the vector method. Okay? So now let's proceed with the non-concurrent force system. So not all forces intersect at the same point. So let's have an example. So as you can see here, these are three forces. They are coplanar, meaning they are in same plane or they are 2D, but they don't have a common point. So that's why they are non-concurrent. However, this is a special case wherein the forces are parallel. And if this in this case or the second figure shows an erratic direction of three forces, meaning they don't share a common point. They might share, but not all of them. So we will use the general coplanar term for this force system. Okay, so in general, a force acting on a rigid body tends to rotate. So if they are not concurrent and it is acted on an object, they would tend to rotate or translate the body. So as you can see in the figure, this body upon application of force tend to rotate and to displace. So this will move here and then this could rotate. So the force itself is the translational effect of the body, tends to move in the direction of the force, and the magnitude of the force is proportional to its ability to translate the body. So if the force is bigger, the translation or the acceleration would be bigger according to the Newton's second law of motion. Now, let's define the effect of having a force from a point, which is a moment. So the tendency of a force to rotate a body is called a moment. So if you apply the force on this body will tend to move in this direction. So that is a moment because it causes the object to rotate. So let's analyze the effect of force on an object to cause a moment, letting F be a force along its line of axis and O a point that is not on the line of action of F. So F will cause a moment at O. Note that force F and the point O determine a unique plane, where we let A be any point on the line of action on F and define vector R to be a vector from point O to point A. So we let an arbitrary point A anywhere on the line of action of force, and then you connect point O to point A and represent it as vector R. So again, you choose any arbitrary point along the line of action of the point, and that point should be connected from O to that point and represent that vector using vector R or small r. So the moment of the force about point O now is called, point O is called the moment center, and the moment of the force F about point O is defined by its cross product. So the moment MO caused by vector force F is the cross product of vector R and the vector F. Note that the moment about a point has the dimension in SI like Newton meter, because force is force times distance, so that is moment. Now, from the properties of the cross product, two vectors, uh, if you get the cross product of two vectors, you have um, a product that is another vector that is also orthogonal to the two vectors. So if you want to review on that, I have also uploaded a video about multiplication of vector. So if you multiply vector r and vector f, there is a cross product that is orthogonal. So as you can see in the figure, this is the product of r and f. This is orthogonal to r and f. Orthogonal, which means this forms 90 degrees to both r and f. Now recall the magnitude of cross product of vectors. So the cross product of vectors, the magnitude of that, the magnitude now of the vector MO caused by the cross product R cross F. So vector MO is the cross product of R and F. And if you want to get the magnitude of MO, recall that the magnitude of a cross product is RF sine theta. And as you can see, R sine theta is D, where D is the perpendicular distance of F to point O. No? And the perpendicular distance from the moment center is the line of action of force D. We could now say that D is R sine theta, and that the value or the magnitude of moment caused by this force is equal to the force or the magnitude of force times the perpendicular distance D. This is because R cross F, again, R cross F causes or gives us the answer vector MO. The magnitude of vector MO is also the magnitude of the cross product of R and F. And recall that the cross product of R cross F, or the magnitude of the cross product of R and F, is RF sine theta. And as you can see, R sine theta is D. Therefore, the magnitude of MO or the moment caused by F about O is simply the magnitude of F times the perpendicular distance. Now, it is strict that to get the moment induced about by a force to a point, it should be multiplied by a perpendicular lever arm. So as you can see here in the figure, we have a force 100 Newton. Now, the force 100 Newton is 2 meters away from O, and that 2 meter is the perpendicular distance of vector, the first vector 100 Newton. Now, it caused a moment MO 200 Newton meter. Now, as you can see, vector MO is acting or rotating about the z-axis. Vector MO is rotating about the z-axis. And moment vectors could be represented by two arrowheads, as you can see in this figure. Now, if this force 100 Newton is causing point O to rotate counterclockwise and using right hand rule, we can say now that this 100 Newton force causes a positive moment about point O because it causes point O to rotate about z-axis by complying to the right hand rule. So if you try to align your right hand to the z-axis or your thumb pointing upward or along the positive direction of the z-axis, your other forefinger is in the direction of the positive orientation, that is counterclockwise. That's why a force that causes counterclockwise rotation about a point is a positive moment. Vice versa, if the force is in this manner and it causes, if the force is directed in this manner and it causes clockwise movement, that is a negative moment. So in this case, for the sign convention, this is a positive moment because as you can see, this rotates, the 100 Newton force rotates point O in a clockwise manner, which is against the right hand rule. So it is represented this way, two arrowheads. And the moment of a force about a point is equal to the sum of the moment of its component. So for example, we have three force vector, F1, F2, and F3. So the sum of the moments about a point O for the three forces, so F1 causes moment at point O, also F2 causes moment at point O, and F3 also causes moment at point O. Now to get the total moments acting at point O, we simply need to get the summation of R cross F. Now, since these three forces F1, F2, F3 are concurrent, we can say now that R cross F1 plus R cross F2 plus R cross F3 is also the summation of R cross F, which is also the total moment acting at point O in vector form. And using the properties of cross product, we can say now that MO is equals to R cross F1, F2, F3, or simply R cross R. Therefore, if we get the resultant of the force and multiply it, we can get MO. And by vector method, if we have vector R and vector F, if we have vector R and vector F, we can get the moment vector induced by or caused by the line of action or caused by a force F. So to get that, we need to recall that R cross F could be represented by matrix. So if you want to review or to understand this part, I have already uploaded a video about how cross product is represented by a matrix. So R cross F is also equal to this matrix. Now, the first step when we are using vector form is to write the force in vector form. So that's the first step. Next is to choose value of R. So if you're choosing the value of R, make sure it is from point O to any point along the line of action of force. So again, R is from point O to any point along the line of action of force. So you have now vector F or the force vector and the vector R that is from point O to any point along the line of action of F. Now we will use this equation shown above to get now the value of MO. Now for the scalar method, we can simply get the moment of a force by simply multiplying its magnitude to a perpendicular distance. But the problem is, if it is hard for us to get the value of the perpendicular distance, we can resolve the equation or the force to a point wherein we can determine the perpendicular distance. For example, we have force F here. We want to get the moment of this force F about this point. But the problem is we do not know the perpendicular distance. So we can resolve this one into Fx and Fy. Now, Fx has a perpendicular distance to this point, which is equal to dy, and Fy has a perpendicular distance about this point, Ex. Therefore, the moment that is supposed to be force times the perpendicular distance could be rewritten in this manner for the ease of computation, wherein m is equals to its component Fx times the perpendicular distance and another component Fy times dx. Now, if we have three arbitrary or erratically arranged forces, it has a resultant, a magnitude of resultant, and a couple resultant, meaning the resultant causes rotation about O, and that resultant could also be force times distance. So for general coplanar force system, we have their equivalent force couple system, and resultant is a force or a couple. So to satisfy the equilibrium of a general coplanar, the x component of the resultant, or Rx, is the summation of forces along x, Ry is the summation of forces along y, and summation of moment about O is the resultant times the distance of the resultant. So for the equilibrium analysis, as you can see in the figure, summation of forces is equal to 0, and also summation of forces along y is 0. But as you can see, the summation of moment is not equal to 0. Therefore, this body is not in equilibrium because this will rotate, this object will rotate. But it is said that to have equilibrium, or to satisfy equilibrium of the body, the three equations should be satisfied. So summation of forces along x equals 0, summation of forces along y equals 0, and summation of moment equal to 0. Now let's have an example. We have here three forces on a similar plane. As you can see, they are not concurrent, or they do not meet at a common point. Therefore, we use the analysis of general coplanar. So using vector method, let us represent all forces in vector form. So let's one by one represent each forces in vector. So to represent F1, we have its x component, that is 30 cosine 40i, and its y component, that is 30 sine 40. Now simplifying that, we get F1 equals to 22.9813i plus 19.2836j. So there we have vector F1. Next, vector F2, we have negative 30i, and for vector F3, we have negative 50j. So our next objective is to get the value of vector R for each of the forces. So for F1, let's have R1. So R1 is 4i plus 3j. So again, if you have problem coping with this one, make sure you review the video. So R1 is equals to 4i, that is simply 1, 2, 3, 4, and plus 3j, 1, 2, 3. So there you go. R1 is 4i plus 3j. Now for F2, the corresponding R is R2. We have 2i plus 2j. And for R3, we have 0i because there's no... 3i and 0j because there's no displacement in y. I mean, there's no... from point O to the point in the line of action of F3 that we selected, there is no change in y. So that is only 3i. Now recalling or writing them up, we have F1, R1, F2, R2, F3, R3. We now need to get MO by performing the formula. Recall that MO is simply the cross product. So the cross product of R1 and F1 is the moment given by F1. So let's start with the moment given by F1. So by using this equation, substituting x, y, z of this R, which is 4, 4, 3, and since this is planar, therefore we do not have z component, and f, that is fx, and fy. Now getting the determinant of this matrix, I have also discussed this in my previous videos, we get m1 equals to 8.1905. Recall that the cross product of two vectors is also another vector. As you can see, the answer is m1 is vector m1, and vector m1 is 8.1905k. So to get the magnitude of vector m1, we have magnitude of vector m1 equals to 8.1905 kilonewton meter. So that's only for force 1. Let's proceed with m2, and still satisfying this formula, we simply substitute the values of these ones. So x now is 2, and y now is 2, and k is 0. For this one, we have negative 30, and 0 yung 0j and 0k. We now get vector m2 equals to 60k, and the magnitude of vector m2 is 60 kilonewton meter. And the same process applies for m3, and substituting x 3, y is 0, k is 0, and for this one 0i and negative 50j and 0k. Now getting the magnitude, getting vector m3, we have m3 equals to negative 150k, and the magnitude of vector m3 now is negative 150 kilonewton meter. Now, adding up the magnitudes of m1, m2, and m3 yields to the magnitude of the total moment caused by the force system about point O. Now, adding up the magnitudes, we have 8.1905 plus 60 minus 150. Therefore, the total moment induced by the general force system about point O is negative 81.8095 kilonewton meter. Now, if you find it too hard to analyze, we still have another option, that is the scalar method. But first, we have to get, or we need to determine the result. The next problem will be about the magnitude of the resultant force. So we have now the moment of the three forces. Now we are asked what is the magnitude of these three forces. So to get the magnitude of the resultant of these three forces, we simply need to get the sum of the three forces. So to get that, we add F1 plus F2 plus F3. Now adding all these forces is simply by adding the coefficient of base vector I. So we have negative 7.0187i plus you add up all the j, so we have negative 30.716 for j, and we don't have the value for k. We now have the resultant r as the sum of all the vectors f1, f2, and 3. So r now is equals to negative 7.0187i minus 30.7164 j. Now, we have only the vector, but we are asked about the resultant, or the magnitude of the resultant rather. So to get the magnitude of the resultant vector r, we simply get the sum of the squares of its component, and getting the square root, that is square root of negative 7.0187 squared plus 30.716 squared. Now the value of the resultant is r equals to 31.5080 kilonewton. Now, how far is the line of action of the resultant from point P? So, if what is asked is the location of the resultant, how far is the resultant from point O? So, if we have the moment equal to negative 81.8095 and the magnitude of the resultant equal to 31.5080, and we have discussed that the moment induced by the resultant about point O is simply the product of its magnitude and its perpendicular distance. Now, D will tell you how far is the resultant from point O. So, from this equation and substituting all the given data, or substituting all the known data, let's substitute MO to the equation and substitute R to the equation. We can now solve for the distance of the line of action of resultant force about point O. So solving for D, we have 2.5964 meters. So we can say now that the resultant is 2.5964 meters away from point O. Now let's try solving the whole problem again using scalar method. So the first thing is to get the moment induced by each force. But the problem is that force 1 is kind of hard to evaluate because of the perpendicular distance from point O. However, we can resolve F1 into its component. So for the x component, we have I'm sorry, we are asked here the resultant force. So let's start by getting the x component. So the x component of F1 is 30 cosine 40. That is 22.9813. We have already discussed how to get the x component. And the x component of F2 is negative 30. The x component of F3 is 0 since this is directed downward. So we have now all the x components. Now we get all the y components. The y component of F1 is 30 sine 40. The y component of F2 is 0 because this is directed to the left. And the y component of F3 is negative 50 because this is directed downward. Now we get the summation of forces along x by adding up all the x component, and similarly we get Fy by adding up all the y components. And to get the resultant, we use this formula. The square of the components is equal to the square of the resultant. So we have now negative 7.0187 squared plus negative 30.7164 squared is equals to r squared. Now, the magnitude of the resultant is equals to 31.5080. Now, you have to check this one with the vector method and they have the same answer. So, using scalar method, we are now asked to get the total moment caused by these three forces. So recall that moment is force times distance, but again, I have already discussed that F1 would be quite difficult to evaluate because of the its perpendicular distance to point O is not directly shown. We can use trigonometry, but it would be quite tedious to get the perpendicular distance. So I guess it is practical for us to resolve F1 into components. Okay, so let's resolve F1 into F1x and F1y, and then we can now say that the total moment acting at point M is F1y d1y. So d1y is simply the distance of F1y from point O, or the perpendicular distance of F1y to point O. So that is 1, 2, 3, 4. So d1y will be 4. How about F1x? The perpendicular distance of F1x is 3 from point O. So it's either we use this F1 or we use its component. If you use the component, make sure you eliminated F1. But if you use F1, make sure you eliminated the components to avoid redundancy. Now, since we have chosen to resolve F1 into components, we can now get the total moments acting at about point O by summing up all the forces that causes moment. So let's start with F1y and its perpendicular distance. So as you can see, F1y causes point O to rotate counterclockwise, that is positive, and F1x causes point O to rotate clockwise, that is negative. F2 now causes point O to rotate counterclockwise, that is why this is positive, and F3 causes point O to rotate clockwise, so that is negative. Now, substituting values from the above equation, so substituting values here, we have F1y is equals to 19.2836, so that is simply the y component of F1, so that is 30 sine 40 times d1y. So if you try to see, d1y is 4, d1y is 4 because this has 4 units and F1y is here. So the perpendicular distance of F1y is here. And minus F1x. So F1x is in this direction and the perpendicular distance is 3. So we have here 22.9813 times 3, but don't forget the negative sign because it causes clockwise direction at point O. And substituting F2, that is 30 times 2, and F3, 50 times 3, we get now the total moment about point O equal to negative 81.8095 kilonewton meter. Now, I have completed now the optimization problems, and for you to have that additional kick for this topic, you might want to ask the problem sets shown in the screen. So if you want to pause this one to answer the question, so I advise you to answer the questions. So these are some of the problems I have prepared or collected, and also here. And for the figures, for the corresponding problems, here are the figures. Okay, those are the other figures. Okay, so thank you for watching my video. I hope you learn a lot about this topic, and please wait for the succeeding topics of this lecture series in static of rigid bodies again. Thank you.